The topic of the video is the partial wave analysis in scattering theory in quantum mechanics. Let us consider the collision between two particles with zero spin and with lower speeds that are in non-relativistic regime and with masses m1 and m2 as shown in the figure here, where r1 is the location of the first particle and r2 is the location of the second particle. If the interaction potential is time independent, then the wave function for the two particle system can be taken as psi r1 r2 and time t is equals to some phi r1 r2, that means which depends only upon the spatial parts, spatial locations of the particles, and then exponential minus I e t or h cut. Then we see that the Schrodinger's time independent wave equation will look like h phi equals to e phi, where h is our Hamiltonian of the system, which is the kinetic energy of the first particle and then the kinetic energy of the second particle and the potential energy of the two particle system. We actually deal with the potential which will have dependence upon just the separation of r1 r2 vectors. And in case if we make a transformation of coordinates from r1 r2 to small r coordinate, which is the difference of r1 and r2, and then the big R coordinate, which is m1 r1 plus m2 r2 divided by m1 plus m2, which is called the center of mass coordinate, then we can see that the potential energy, which is v r1 r2, can be just a function of v of r, which is the length of this vector r. And we'll also see that minus h cut square by 2m1 del square operator for the first two particles coordinates, the position coordinates, and then minus h cut square by 2m2 into del square operator for the second particles position coordinates will be equal to minus h cut square by 2 big M, where big M is total mass of the two particles, and del square operator for the center of mass coordinates, and then minus h cut square by 2 mu, which is the reduced mass, which is m1 m2 divided by m1 plus m2, into the del square operator for the relative coordinates. So after the transformation, the Schrodinger's equation will become this form, and to solve this Schrodinger's equation, we can actually take the solution phi r and big R as a product of chi, which will depend only upon r, into psi, which will depend only upon small r. And then if you substitute this into the above differential equation, we can see that this del square will operate upon only the r coordinate. So psi will be actually kind of constant for this because it has dependency upon small r. So we can write this thing as a constant outside. And in the second term, we'll be writing chi of r as a constant because this del square operate upon only the smaller coordinates. And then the third term will just have v of r into chi into psi, and on the right hand side we'll see that it's equal to e times chi into chi times psi. And if you divide this entire equation by the product of chi and psi on both sides, then we see that here psi and psi will get cancelled, so chi will remain in the denominator, and then in the second term chi and chi will get cancelled out, so we'll have psi in the denominator, and in the third term we just have only v here, and on the right hand side we'll just have e. And if you take this right hand side stuff, which is e, as e of r, e sub r plus epsilon, such a way that this minus h cut square by 2 big M into chi into del square, which operates upon only r into chi, is equals to e sub r. Then we'll have the remaining terms, which are minus h cut square by 2 mu psi del square for r coordinates into psi plus v is equals to epsilon. And if you rearrange this equation, we get this form, and then if you call this del square del square r just del square, then we get this differential equation as equation number 1. And we can solve this in spherical polar coordinates because the potential v is just a function of r, so we have got a spherical symmetric potential here. So we can use spherical polar coordinates to solve this differential equation number 1. And in the spherical polar coordinates, the del square function is minus 1 over 1 over r square into dou by dou r of r square into dou by dou r plus 1 over r square into sin theta into dou by dou theta of sin theta dou by dou theta plus 1 over r square into sin square theta into dou square divided by dou phi square. So if you substitute this into equation number 1, then we see that it's equals to this form. And to solve this again, we can actually take the solution for psi of r now, which is a function of r theta phi, as a product of r, which depends upon only upon r coordinates, and y, which will depend upon theta and phi coordinates. So if you substitute this into the above equation, the first term will have dou by dou r, so it will only operate upon r coordinates but not on y, so the y will remain as a constant outside. And in the second term, this r will remain as a constant because the differentiation is happening with respect to theta here, so it will operate upon only y. And in the third term also similar kind of logic, so r will come in front as a constant, but dou square by dou phi square is operating upon y. And in the term which has got this v into psi, we can write v into r into y, and on the right hand side we can write epsilon into r into y. So if we divide that equation by the product r into y on both sides, then we can see that y gets cancelled in the first term, and we get r in the denominator, and in the second term r gets cancelled, but we still get y in the denominator. And if you write the second and third terms together, we can write this bracket here, and here v will remain because r into y will get cancelled, and on the right hand side we'll just get epsilon. And if you call this stuff in the bracket, which is 1 over y into sin theta into dou by dou theta of sin theta dou y by dou theta plus 1 over r square into sin square theta into dou square y by dou phi square as minus L into L plus 1, then what we see is that this y theta phi will be spherical harmonics, which is just ylm theta phi. And the radial part of the wave equation will become this. And if you rearrange this to write d by dr in place of dou by dou r, because now r has dependency upon only just r, then we get this equation of this form, which we can call as equation number 2. And to solve this differential equation, we can call u of r is equals to some r into big R. Then we'll see that d by dr will be d by dr of u by r, which is this, and then we can say that r square into dr by d small r will be small r into du by dr minus u. And if you do d by dr of r square into dr by dr, that's because we got all the stuff in the first term of this equation number 2. So if you do that, then we'll see that r into d square u by dr square plus du by dr minus du by dr, so these two terms will get cancelled. So we can just write this first term is equals to r into dou square u by dou r square, and if you substitute this in the equation number 2, then we get this equation. And if you just write the first term with d square u by dr square, that means we divide this entire thing by r, then we get this equation. And for the region where v of r can be ignored, and if you call 2 mu epsilon divided by h square as k square, then the differential equation can be written as d square u or dr square plus k square u is equals to L into L plus 1 divided by R square into U. So if you actually bring L term towards the left hand side, and if you send the U term towards the right hand side, then we can rearrange this differential equation as equation number 3. This is actually kind of equation for spherical Bessel functions. So the solution for this differential equation number 3 can be actually a linear combination of spherical Bessel functions JL and NL as u of r. So we can write u of r is equals to some constant a into r into jl k of kr plus b into r into nl kr. But these functions jl or nl are not spherical waves. So we select a linear combination of these things such a way that JL plus X plus I into NL X is equals to some function called H sub L superscript 1 X, and then the other one is JL minus NL as HL2, and these HL1 and HL2 are called spherical Hankel functions of first kind and second kind. But at large value of r, these functions can be written, I mean the h1 kr can be written as e power ikr divided by r, and h2 kr can be written as e power minus ikr by r. So since we need a solution of outgoing spherical waves, that means the physically meaningful solution seems to be coming from h1 kr but not from h2 kr. So we retain only the h1 kr terms in our solutions and we ignore the h2 kr terms. So we can write our u of r is equal to some constant c into r into hl1 kr, and we can write this r of r, which is u divided by r, as a c into hl1 of k of r. Therefore the scattered waves wave function can be written as psi r theta phi is equals to the constant c into hl1 kr into ylm theta phi. And for asymptotic limit, we can write the scattered wave function as some constant a into the incident plane wave, which is exponential ikz, plus the linear combination of all possible values of l's and m's. That means the summation over lm, and then the constants could also depend upon lm, so we can take c sub lm, and then hl1 kr into ylm theta phi. Since this HL1 KR is actually kind of equal to minus 1 raised to L plus 1 into exponential IKR divided by KR, we can actually express the wave function as this form. I mean, in the second term, we get 1 over K into summation over Lm into minus 1 raised to L plus 1 CLM exponential IKR by R into YLM theta phi. And if you compare this wave function to psi is equals to a into exponential ikz plus f theta phi into exponential ikr by r, then we see that the scattering amplitude being equal to 1 over k into summation over lm minus 1 raised to l plus 1 into clm ylm theta phi. And here these clms are called amplitudes of the partial waves, which are ylm theta phi's. And then the differential scattering cross section is just d sigma by d omega, and equal to modulus square of f theta phi. That means we can write f star into f. So, and for f star into f, we can express one of them in lm's and then the other one in l prime m prime dummy coordinates, I mean dummy indices. So we get this equal to 1 over k square into summation over lm, and then another summation over L prime M prime. Of course, this summation itself is a double index summation, and then the other one is also double index summation. And then we can write minus 1 raised to L plus L prime plus 2, and then CLM star, which is a complex conjugate of CLM, and then CL prime M prime into YLM whole star, and then into YL prime M prime. And the total differential, total scattering cross section sigma is equals to the double integral, which is for theta and phi, of d sigma by d omega into sin theta into d theta d phi, which is this element of solid angle. So if you do this thing, and if you make use of the fact that these YLMs are actually orthonormal functions, so this will actually give us 1 over k square into summation over lm into modulus square of CLM. That's it in this video, and thanks for watching.